complete the discussion on backpatching. So let us quickly recap what we have done so far during the intermediate code generation. So what we have done is we have seen what are the main methods. So we have seen that 3-address code is a very good starting point. And there are quadruples, triples, and indirect triples. We have seen the differences between them, and I have asked you to look into the merits and demerits of these representations, which is a good common question for the semester. You will get 4 marks, maybe 3 to 4 marks. Then we come to the actual problem, which is how to generate this kind of 3-address code. And we have used lots of assumptions: s.code, e.place, e.code, new temp, new label, synthesized attribute, inherited attributes, all that, those kind of things, which you have learned from syntax-directed translation. Then we went to different types of programming constructs and we have seen how to actually do the translation. So we started with the declaration type, and please look into these things again and again so that you kind of remember this thing. Although once you are familiar, you will be able to write your own rule without really looking into them. Then we came to the assignment statements, mainly the arithmetic statements. Then we went to the Boolean expressions, and we said that we can actually translate Boolean expressions either using numerical way or flow of control way. Of course, flow of control way is the better one, because then it will be easily merged with the translation of real flow of control statements in programming languages. So Boolean expressions are basically the enablers of flow of control statements, but then translation of only the Boolean expressions can also be done in a flow of control manner, and that can actually really merge well with the flow of control constructs in programming language. And we have seen both numerical Boolean expressions, and we have seen how to translate them in different types of 3-address codes. Then we have seen the flow of control way of translating the Boolean expressions as well. Here we were using some new attributes, e.true and e.false as well. These e.true and e.false are nothing but targets where control will be reaching once the logical expression evaluates to true or false. So mostly these are generating labels. And that's where the problem comes, because when we do the translation, we can observe that very often when we actually want to generate e.true or e.false, the actual target is not determined as yet. So that is where translating Boolean expressions and flow of control statements are much more difficult than ordinary arithmetic statements. Then we saw some logical expressions consisting of relational operators like or, and, etc. And then we have done a translation of one of the expressions which we did for numerical way earlier. And we have seen that it is actually much more compact. We can easily combine the translation of relational or Boolean expressions along with the logical connectives. Okay, so we just need to generate the corresponding labels, and as you can see, very often those labels are not yet known when the translation completes. Like in this case, you can see that you produce the false for a smaller than b, but not the true, not the target for true branching. So we have kept L true, which is left unspecified. Similarly, for C smaller than D, the E dot true is known, which is known to be L2, but not E dot false, which is given a value L false, which is not yet determined. Yes. Yeah. No, can't you see this screen, which is the PPT? Why? Let me see why it is not coming. Can you see now? Okay. So this is where we are doing the flow of control way of translating the Boolean expressions. As you can remember, we have already covered it. Then we come to the actual flow of control statements, which is uh, basically mainly to combine with the logical expressions we have already translated. So we don't have to do too many things differently. But certainly what needs to be done is generating the targets. As we have seen earlier, when we only translate the logical expressions in flow of control way, sometimes the E dot false or E dot true are not known. But the moment these logical expressions, you know that these logical expressions in general are used with flow of control statements in a programming language, like for example, while or if or for, like that. So the moment you combine these logical expressions with flow of control statements, then these flow of control statements can actually guide where the E dot true and E dot false would be there, along with something else, which is S dot next, because the flow of control statements are generally of the form, say, if E then S or while E then S. So statements are there. These statements are generally assignment statements. Uh, so if you can translate these flow of control statements, very often these E dot true, E dot false, S dot next, these are guided by this flow of control statement translation. So you can actually complete the translation easily. We have seen that uh, E dot true and E dot false, we have seen these are basically the inherited attribute way we have translated. And we have seen that that can cause some problem at times. We'll come to that again. That is actually the important topic for today's class. These are mainly for recap purpose. Then we come to the actual flow of control statements, which we are dealing. As you can see, if E then S1, or if E then S1 else S2, and while E do S. So any S, which is a flow of control statement, can translate to any of these rules. And we have seen some of the translation schemes like E2, how can we get the E dot true and how can we get S dot next and stuff like that. Similarly for while E do S. So this is something we have already done, and we have done in a translation as well of this particular statement. So while A smaller than B do, if C smaller than D, then something else something. And the translation scheme here, please try to remember this as well, and then you will be definitely able to change or create something else which can be even better. So these are the production rules for flow of control statements. Now, one of the main problems we have seen that if, okay, let us read through this again. We started this, but we could not complete. So the easiest way to implement the syntax rejected definitions is to use two passes. Why? Because during the first pass, you can generate E dot true and E dot false, but not all of these values are well known. Okay. So you can leave them unspecified. And then if you scan the whole thing again, then E dot true and E dot false will be actually getting their targets. So two passes is very good. So that is what they mean. First, construct a syntax tree for the input. Then walk the tree in depth first order, computing the translations given in the definition. So in this case, when you are constructing the syntax tree, you can easily, since we are always using a bottom-up parser in our course, so when you are constructing the syntax tree in a bottom-up manner, all the synthesized attributes are well known, but the inherited attributes are not. So then once you do that, you come from the root and in a depth first order, you traverse the tree, then you'll be able to complete the inherited attributes as well. So 2 pass is good enough. But can you do in a single pass? Because these passes are very expensive in terms of time. Why? Because your program can be millions of lines of code. So if you are uh, actually doing one pass, there is a good possibility that a big part of the intermediate code will not be in memory, but it will be on the disk. So you have to use the virtual memory kind of thing to get part of the intermediate code in memory and then process it, and then you have to dump it into the uh, secondary storage and then bring in the remaining part. So this kind of thing can take a lot of time. So if you are doing another pass, it's just going to double it. Even though the complexity doesn't really increase, it's just a constant complexity increase. But since each of these passes are themselves very expensive, maybe taking of the order of a few seconds also, it is not advisable to, it's probably desirable to have only a single pass. Okay. So problem with a single pass, as you know, is generating code for Boolean expressions and flow of control statements, as we are repeating, because during one single pass, we may not know the labels that control must go to at the time the jump statements are generated. So those go-to statements or if conditional go-to statements, those labels will be unknown. So what we can do is we can generate those statements, those jump statements anyway, and temporarily leave the targets unspecified. Okay. Then each such statements where the go-to statements, where there is a list of go-to statements and labels are not yet filled in, this can be determined later on, but not in a different pass. During the same pass, using some intelligent translation mechanisms, we can fill it in. And this is known as the backpatching technique, which is very interesting. So what is the main thing? The main thing is that if you remember from syntax-directed translation, what we were doing for inherited attributes to be translated during bottom-up parsing is that we were keeping marker non-terminals. So by bringing in marker non-terminals, we eliminated the necessity of embedding the code inside a production rule. We could still use actions where where we still use actions at the end of each and every production rule by suitably inserting marker non-terminals. If you can remember, same technique is used in backpatching. So here, whenever there is a possibility of a target which may be unspecified during the first pass, a marker non-terminal is kept. The only task of this marker non-terminal is to produce an epsilon. So it does not really uh, change the translation scheme, but what it does is it keeps a track of its current quadruple number, and we call it as m.quad. So whenever m is translated, at the end of the translation, the action is essentially m.quad is next quad. We'll see, we have another marker non-terminal today, which will do something a little different for a particular reason. So that essentially stores the target quadruple number. And whenever it is needed, via this backpatching, we can we can fill in that target. So this is what backpatching does. We'll see an example today itself. So now we'll need a few more things called make list I which creates a list of quadruple, new list of quadruple. March P1, P2 adds a new list of quadruples to P2 to an existing one P1, and then backpatch P comma I. What it does is the first parameter P is a pointer to the quadruples, or pointer to the list of the, or is a list pointer to the quadruples. Each of these quadruples where the go-to address is unspecified should be populated by I. That is the target. So this new internal function we'll be using, and the meaning is clear now. Now what we did is we did a translation for these guys. First we'll do the Boolean expressions, and then we'll just touch the flow of control. Unfortunately, I don't have enough time to show a detailed example of flow of control statement like I did earlier. But when we have a Boolean expression, let us see how we can do the translation. So here you can see E1 or E2. E produces U1 or E2. So there is no problem with U1, but after U1, where E2 starts, that should be marked. That's why you can see E2 is preceded by M. And as you can see, M does nothing but produces an epsilon. The corresponding action is M dot quad is next quad. That means it stamps, it records its current quadruple number. So you can readily understand U1 dot true or U1 dot false can point to this thing. So you can easily backpatch U1 dot true or U1 dot false into this. Also, instead of U1 dot true or sorry, E dot true, we are using something else which we call E dot true list and E dot false list. The difference between E dot true, E dot false, and E dot true list and E dot false list is that we have intentionally made these true list and false list parameters as synthesized attributes. So they will get populated. So they can get populated during the bottom-up translation. So as code is generated for E, jumps to the true and false exits are left incomplete. The label field is not yet filled. Then these incomplete jumps are placed on list pointed to by E dot true list and E dot false list. Then we do backpatching to populate it. That's it. So it can be done in the same pass, because backpatch takes the list. So whenever you call backpatch, it will go to those quadruples which are pointed to the by that list and populate the values, populate the target values. So let us see an example. Okay, E1 or ME2. So in this case, your E dot true list is nothing but merge E1 dot true list and E2 dot true list. So that means whatever is pointed to by E1 dot true list is the same as E2 dot true list. So you can merge them and make E dot true list point to that as well. Whereas for E dot false list, it is nothing but the E2 dot false list. As you can see, these attributes are synthesized attributes compared to the inherited attribute E dot true and E dot false, which we were using earlier. In case of AND, it is just a little different. E dot true list and E dot false list just changes their position. In both cases, you can see the backpatch. What it does is, in case of OR, E1 dot false needs to be E1 dot false list needs to be backpatched to M dot quad. In case of AND, E1 dot true list needs to be backpatched to M dot quad. There is nothing to be done in not or parenthesis. But when you have a relational operator, ID1 relational of ID2, you can see that you have to generate two statements. If ID1 dot place relation of ID2 dot place go to, then the target is unspecified, and then go to unspecified. So the first one is for true statement, and the second one is for the false statement. Okay, this is something we have already done very similarly. Here, instead of e dot false or e dot true in goto, we are leaving an unspecified thing. Now, the good thing here is that we are generating a true list and false list, new lists from here. You can see nothing, nowhere else this is generated. This true list and false list. This true list and false list are generated only in these relational operators. I'm ignoring e producing true and e dot false, e producing false. These are ignored. So I assume that there is no such thing as true or false in our programming language, but true and false is evaluated only based on the relational operator. And then the logical connectives keep on building on that true and false values. Okay. Now, we have this A smaller than B or C smaller than D and E smaller than F. So let me translate it in our new way. Okay, as you can see, A smaller than B or C smaller than D and E smaller than F. We have already done this exercise using the numerical way. Now here, what we need to do is we'll translate it according to the new scheme with backpatching. So a single pass is sufficient. Okay. So now what we'll do is we'll start the translation from quadruple number 100. We'll assume it. So what is the translation scheme for this guy? So as you have seen, e dot true list and e dot false list should be created with the next quad number. So next quad is 100 now. So e dot true is 100 and e dot false is 100. I'll use e dot true and e dot false instead of e dot true list and e dot false list all the time. So, or maybe e dot TL and e dot FL. So TL here is 100 and FL is 101. This is one translation for this guy. So E dot TL is 100, E dot FL here is 101 for A smaller than B. Now, what are the other things? The other thing is that you have to emit those two statements corresponding to the true and false of these relational operator. So you can write this: if A smaller than B, go to and 101, go to, again, these things are unspecified. Now note what? Yeah, that's it. Nothing else is there. Okay. Now we'll come to C smaller than D. So in C smaller than D, we'll have a similar translation. This is E. I think up to here it is clear. So now I have translated C smaller than D into E. And similar translation for A smaller than B happens. So I need to create the true list and false list as well. Okay. But there is something else. What is that? As you can see, since we are using an OR between this A smaller than B and C smaller than D, so this rule triggers in E1 or ME2 to create an expression. Okay. Okay. So saying that, we are not yet done here. So I'll come later on. Okay. Because this is not yet done. We are just trying to parse the string, which is consisting of only of terminals. So right now we haven't gone to OR. In fact, we have gone to OR, right? Yeah. So you'll see A smaller than B, OR. Okay. So this is there. Okay. So this is already seen, and then we come here. So this much is done. This left E is done. This OR is parsed, but it's not done. It's not done yet. So reduction hasn't taken place. It's waiting for further things. Assuming AND is having higher priority, we'll see that this reduction will happen at the end. So second E in the middle, so we can create the true list and false list for this guy. PL is 102 and FL is 103. So this is done, and the corresponding actions are taken. Okay, then AND comes. So AND is taken care of. And then we come here. This is the third E. And corresponding true list and false list is 104 and 105. Yes, 104 and 105. Now, you can translate the remaining things here. Simple. If E is smaller than F, go to unspecified, and at 105, go to unspecified. That's it. Okay. Now comes the next part of the translation, which is we should be reducing E and E into E. And what is the rule? The rule is E produces U1 and ME2. Okay. So U1 and ME2. So M is coming into picture now. So we'll have this. And that means we have a M dot quad. So the Q will be, what is the Q? M dot quad is next quad. So M dot quad is nothing but 104. Okay. So whenever this reduction happened, M produces epsilon. M dot Q is set to 104. Note that this is not a list. This is a single number. Okay. So now this whole thing, E and ME, will be reduced to E. Okay. Assuming AND has a higher priority than OR, just what we did earlier. So what is the translation rule for that? As you can see, E dot true list becomes the true list for E2, because only if E2 is true, then E1 is true. Assuming we have already evaluated E1 true, E1 dot true. So just by checking the E1 dot true list is not going to help. We assume that E1 is true and then only we'll check E2. So whatever is in the true list of E2 can be passed to the true list of E. Since this is a synthesized attribute, this can work. False list would be a merging of the false list of E1 and E2, which is expected. Okay, so let us complete that part of the translation. So here, the true list is E2 dot true list, so which is 104. And what is the false list? False list is a concatenation of true list of the left child and true list of the right child of E. So as you can see, the false list of left child is 103. So 103 should be there, followed by the false list of right E, which is 105. So this is the false list of this guy, this E, right here. This E has true list as 104, but false list as 103 and 105. Now what? The action says backpatch U1 dot true list to M dot quad. That is another action. Okay. So backpatch U1 dot true list. We already have U1 dot true list. What is U1 dot true list? 102. So we'll backpatch. We'll go right here. This 102, and we'll say this is where the backpatching will go. So we'll backpatch U1 dot true list with M dot quad. What is M dot quad? 104. This is how backpatching eliminates the unspecified targets. Okay. So 102 is now filled in. This target is filled in. As you can see, if C is smaller than D, it will go to 104 to further check whether E smaller than F is also true or not. Okay. So this part of the translation is done. Now we have to reduce further this leftmost E or and E. So there is an M M somewhere here. So there should be an M somewhere here, which will produce epsilon. And in the process, it will have its own Q, which is nothing but 102. So M dot Q here is 102. So now we have the complete translation. E or this is M actually. M E. And this is the final reduction at the root level. So now the root level E, what is its TL and FL? Let's look at it. Its TL is, let us look into the translation scheme. As you can see, E1 or ME2. So second action is E1 dot true list. E dot true list should be a concatenation of E1 dot true list and E2 dot true list, and false list of E should be the false list of E2, as is expected with the translation scheme of OR. So E1 dot true list is E1 dot true list is 100, and E2 dot true list here is, as you can see, 104. That is this guy right here. And the false list is, and false list is nothing but a false list of E2, which is 103, 105. So now you have all the targets specified, and you can see that it has another act in the production rule. It has another action, which is backpatch u1 dot false list with m1 dot m dot quad. So u1 dot false list is the statement 101. So this should be getting m dot quad, which is 102. So this much is filled in, and nothing else can be filled in here. So just by translating this Boolean expression, you won't be able to do anything more. So you can see the target for statement number 100 and target for statement number 103, 104, 105. They are all left unspecified. They will be filled in when they will be used in a flow of control statement, which will be using this expression. In fact, that kind of statement I'll be giving you in the assignment so that you can readily understand after you have done all these translations, what exactly happens. Okay. So this is basically the backpatching technique based translation. As you can see, in a single pass, you can more or less fulfill most of the targets. Had you used the actual flow of control statement while E, then S, and E is there, then you could have filled in all the targets, as you will see in your assignment. Okay. So this is done for flow of control, only the logical expressions.
Sir, you have completed the leader part.
No, that will be done in the next class. Okay. And
Okay,
it will be on Tuesday, 10 o'clock. Okay. The timings are a little changed. You can just check the chat box today, what I have said, but I'll be specifying that in a classroom also. Okay. Now, for flow of control statements, I am not going to go into the details. I'll just conclude the class by specifying what they should look like.
Sir, here left recursive or right recursive matter in the flow
Yes.
of control?
Yes, definitely. Definitely. Okay. Okay. All right. Now, here, the only difference with E is that we have S and we have list of statements L producing L semicolon S so that it is very easily backpatched, or L can produce a single statement. So any arithmetic assignment statements, the level of those things or the target of those things can be the target of any of the conditional jumps as well. Okay. So for those things, for S, we need only one thing, which is known as next list. So what follows S? Those list of quadruples should be an attribute for S. Now, you can see the translation of while E do S1. So what are the targets here? As you can see, the target could be before E and the target could be before S1 as well. So we can put two marker non-terminals for needed for backpatching. So we can say while M1E do M2 S1. And the natural translations follows that M1 would be, M should be translated into epsilon, and M dot quad is the corresponding action which will be fulfilled, which will be filled in with the next quad value. Okay. So what is the actual translation scheme? You have to emit, go to M1 dot quad, because you will be coming back with the loop again and again, and you need to backpatch S1 dot next. So what is next of S1? Nothing but M1 dot quad, because it has to come back. And so whatever is the so any of those S1 can be again logical expressions, flow of control statements. So those statements should also come back to M1 dot quad, because that is the semantic action for a while loop. For E dot true, as you can see, E dot true list is nothing but M2 dot quad. So whenever E dot true is to be populated, it has to actually go to the starting point of S1. This is how all those unspecified go-tos in our earlier example will get filled in because exact quadruple of S1 will be known. Also, as you can see, S dot next list is nothing but the false list of E, because whatever is whatever list of quadruples which can be the target of false of E should be where S should be transferring its control once it is done. So this is the translation scheme for while E do S using backpatching. In case of the if statement, if E then S1, there is only one target needed, which is the starting quadruple number of S1. So you can see M is placed before S1. The backpatch definitely will be for E dot true list. So you backpatch E dot true list to M dot quad. And since there is no false part here, we can say that S1 dot next list and E dot false list can be merged to give the S dot next list. So whether E is false or whether you are going after S1, they can be the same thing in this case. In case of if then else, it's much more complicated. So as you can see here, of course, you need to backpatch E dot true list, and also you need to backpatch E dot false list as well. So you put a M before S1. So the statement here is if E, then S1 else S2. So before S1, you should put one marker non-terminal, and before S2, you should put another marker non-terminal. So you can see if E, then M1 S1, forget about the N, I'll come to that, else M2 S2. So the translation is if E, then M1 S1, else M2 S2. Note that we don't need to keep track of the quadruple for E. So there is no M before or after E. Okay, in fact, M should be always before a particular non-terminal. So in case of while, that was needed because while is a loop. So the starting quadruple of E needs to be noted down as well. Here, that is not needed. You just look at E. Depending on the evaluation of E, either you choose the starting quadruple for S1 or the starting quadruple for S2. The first one is for E dot true, and the second one is for E dot false. So you can see you have to backpatch E dot true list to M1 dot quad and backpatch E dot false list to M2 dot quad. This much is easy. Now the problem is, what about N? Why do we need N? Okay. So if control falls out the bottom of S, when S is an assignment, we must include at the end of the code for S1 a jump over the code for S2. This is a problem because you keep on generating the quadruples. If before S2 you have an assignment statement, then if you don't do anything, it will fall through S2 as well. But that's not what you need. That's not what you want, right? You want S2 to be skipped over. So a go-to statement needs to be generated after S1. And exactly that is why we have N. So we need to not only keep track of the starting of S1, but we need to keep track of the ending of S1 as well. This is where we have the marker non-terminal. After the non-terminal, we are trying to backpatch. Okay. So N is also a marker non-terminal, and it produces epsilon as expected, but its task is a little different. What it does is it emits a go-to statement so that S2 can be scooped over. That is the first thing. And second thing is it uses the next list property to create a list corresponding to next quad, which is the statement before S2. And what is this n dot next list is used for? As you can see in the translation for S, after the backpatches of e dot true list and e dot false list, what we are doing is we are merging S1 dot next list with what? With whatever is the next list for n and next list for S2. Why? So n dot next list is basically pointing to the go to statement, which will help us skip over S2. Okay. Now, the S dot next list, as you can see, the S dot next list includes all jumps out of S1 and S2, as well as the jump generated by n. So S dot next list should be consisting of S1 dot next list as is expected. Not only that, it should be the next of both n and S2 as well. And that's why we have merged n dot next list and S2 dot next list first. Then the merge list is merged with S1 dot next list to make sure after S we go to the appropriate place, which is after S1 as well as after n and S2. Okay. This is how you can generate the 3 address code for backpatching, which is ready for backpatching for flow of control statements. The remaining ones are easy. So S could be begin, L, end. L means list of statements. S could be an assignment statement. And list could be, list is basically a recursive call. It is a left recursive grammar, as you can see here, a left recursive one, which is fine because we are using a bottom-up parsing. So L1 followed by S. So each time you call S, the quadruple number has to be noted. So that's why you have an M before each of those S, and it can terminate the recursion using a single S. Okay. So these actions are kind of self-explanatory. So S dot next list is nothing but L dot next list for rule number 6. For rule number 7, this is an assignment. So we start a new assignment where we make a new list, which is nothing but an empty list. And we keep on concatenating this list. How? As you can see in the recursive call L producing L1 colon MS, we backpatch L1 dot next list to M dot quad, and L dot next list is set to S dot next list, which is fine. And these lists will be, so when you have a L producing S, you can see that, in fact, I need to see where we are actually populating, merging something to get a new list. Okay, that I'll explain in a different part. Okay, I'll give you as a note. Okay, how we have to go through an example to complete that. That's about it for all of ICG. So we have learned a lot of things here. Unfortunately, we didn't have a lot of time to cover all the aspects in more details. So please go through the PPT very well. This is quite needed for your exam as well as if you want to understand compilers. And that's about it for ICG. Next week, we are going to start a topic on code generation and code optimization. I'm planning to complete both on Tuesday. So morning and afternoon, there will be 2 double lectures, each 1 hour, 1.5 hour duration. So please be there. And also let me take your attendance today so that